Hi, everyone. This is Pete Schellenbrand. I'm your host for today's webinar on Sine data reduction. Your speaker will be Chris Sensor. You want to say hi, Chris?
Hi, everyone.
That's a very forceful and exciting hi there, Chris. And with that, I'd like to give it over to you, Chris.
Thank you, Pete, for the kind introduction. As Pete said, my name is Chris Sensor. I'm an applications engineer here, and today we're going to talk about Sine data reduction. As the title slide says, I do have a little glossary of terms and abbreviations here. I'm not going to go through all of these. I just included in all my presentations just in case something like this comes up. This is everything we do. We're just going to be talking about test and using test lab software and our SCADAS hardware for vibration data reduction. Where all this comes in is in this vibration portion of qualification testing. Sine data reduction is very typically used in the space industry when we have a whole bunch of channels that we need to deal with. And the controller itself, one, you might want to have a different setup just to manage the channels and be able to see just control and the important things going on in your controller, and then have your data reduction system as backup. You can do response limiting and stuff with online sign reduction. And really what we're doing with this secondary system is taking time histories, and you can use online sign data reduction to supplement the controller and be able to process those time histories live. So it's an added bonus to just years and years ago when we just used to plug these channels into a signal conditioner and go right into a tape recorder and record the raw voltage data.
Tape recorder, you're really dating yourself there, Chris.
I've never used them, Pete.
Oh, okay. Now I'm feeling dated. Go back one slide. I just want to kind of understand this again because I must look. So you got the satellite on a shaker table,
Yeah,
and you excite it with a sine wave, a single frequency, but you change the frequency of it.
you're changing the frequency constantly.
And you're making sure it's at a certain level. So there's like a controller. And then a second system is gathering all that sine data from a bunch of Excels all over that satellite in this case. And
Correct.
those it might process and make FRFs or do things with. Is that?
That's correct. You got it, Pete.
So the sine data reduction is like a second observer on this exciting sine control test.
Okay. It's like having a second observer, and we'll go into a little more detail on how that works. Here we have kind of a typical spacecraft setup where you have your control system, you have your recording or reduction system. These two systems have to be synchronized somehow so that the data reduction system knows what the controller is doing. Typically, that's done with something called a COLA channel, or constant output level adapter. And again, we'll talk about this in more detail. You have all these things going into the controller, different notch channels where you want to limit vibration on critical components of your spacecraft. You might do force or moment limiting, where you have a whole bunch of force washers in the interface between the adapter plate and the shaker, where you're controlling things like overturning moment on the spacecraft. And you limit the force input because of mechanical impedance mismatches between a shaker situation, which is typically much more rigid than what you have in the field. So the input can over vibrate your structure or over test it. So force limiting is a way to take care of that. That's a whole other seminar to talk about that. But you have your control channels that's replicating your vibration environment that you want. And then you have a drive output to your shaker amplifier, which sends this signal and makes the shaker do what you want it to do. And basically the whole idea behind the reduction system is you're reducing the processing that the controller has to do. In years past, when you had limitations in PCs and what front ends can do, this was super critical. These days, we've done a lot of work in hardware to be able to sync many hundreds of channels into one controller, but the legacy is still this data reduction system And a lot of spacecraft manufacturers, when they test, they still like to use this secondary system for a couple of reasons. One, you have a secondary backup, right? So if something goes down over here, you still have data saved away in your secondary system in case of things like catastrophic failure. I would estimate to be less than 1% of cases now where that ever happens these days. But still, the whole idea is we're reducing the burden on the controller and taking all these data channels in a secondary set of hardware. A few notes on Sine control testing. In the time domain, you have something that looks like this, where you have a constantly changing frequency, where you're sweeping between a low frequency and a high frequency, or from a high frequency down to a low frequency. And you excite resonances as you sweep past them, which can result in lots of force. And again, going back to force limiting, important thing in these big satellite tests. But the software has some control algorithms that shape the drive to the response of the system, right? You might have some resonance in your fixture that comes up, and the controller can adapt and overcome to make sure you're keeping to this reference signal. Typical Sine test for spacecraft is in the 4 to 110 hertz range, very typically 5 to 100 hertz. And that's really all we have to worry about in spacecraft for Sine as far as frequency range. But regardless of the frequency range, you can still use these methods for any type of test. The way the control loop works is we have our test object. We're taking in this control signal, we measure the response, and then we do some amplitude estimation. And essentially what this is all about is you never have a perfect sine wave when you do this test. You have to make a decision about what the amplitude actually is on the shaker because of harmonics and things like that. So very frequently this harmonic estimator is used, which essentially is fitting a sine wave to the data coming in to filter and suppress out any harmonics of the main excitation frequency. RMS average and peak all use a block by block method to estimate the amplitude. So things like RMS average and peak are more conservative ways than harmonic, because if you have a high frequency harmonic that's riding on top of the sine wave, your RMS average and peak might be a higher amplitude that's measured than what's measured by the harmonic estimator. So this is an example of that, right? So you have this high frequency noise that's riding on top of your main sine excitation frequency. You have this tracking filter that's going to suppress out harmonics, and then this is what your filtered time history looks at. So all these calculations are done in the time domain, and what essentially we're doing is based on what your amplitude estimation method is. We take a look at this and say, okay, this is what the amplitude is for the controller, and the controller adjusts the drive to keep in your target amplitude. So after we figure out what the amplitude is, then we make a decision about whether we need to stop the test. Are we out of this abort limit that we've programmed in? If you are, then you stop the test. If not, you calculate this inverse transfer function, estimate the next drive amplitude, check all your notching channels, and then start moving to the next frequency and send out this updated drive signal. All this is happening in real time and really, really quickly. You might have been asking yourself what's limiting or notching, as we've been talking about. What can happen is you have some control profile, but you have a component of your spacecraft that maybe has a resonance, like the parabolic reflector or something like that, some type of antenna or electronics box that's going to exceed its maximum tolerances during vibe if you stick to this output profile. So what notching does is recognize that you're going over this limit that you set in the software for your notch channels, reduces the drive at that frequency, and then you have a response that's going to stay underneath the notch profile. So that's notching in a nutshell. Force response limiting, you might be wondering about that. You have, this is a preloaded force transducer. There's also unloaded force transducers that you can get that you have to preload yourself by putting a bolt through. This adapter ring, you can see up here, here's an example of force links that are going to be applied to a structure. This is an example of the force washers that require a bolt to go through and preload the force transducer before applying your spacecraft to this adapter ring. When you set this up in the software, you can calculate for the sum of all the different forces. So in other words, each one of these force links or force transducers has an X, Y, and Z component to it. So what you do is sum all of the X components, sum all the Y components, sum all the Z components, and then you have the resultant forces for each one of your directions here. You can also do that for overturning moments. In this example, overturning over X, overturning over Y. And you can see this calculation is a little more complicated because we're multiplying each channel by a scaling factor. And the scaling factor is based on how far each of the transducers are away from the center of mass. But you add all these up and then you get your overturning moment calculations, and you can apply a profile to each one of these for limiting. Again, this
overturning limit because the satellite overturns from the shaker.
Yeah, essentially what can happen is when you have a tall structure, right? Here's some satellite that's really tall, and you have your shaker here, an adapter ring, and all this stuff. Your CG might be up here on your satellite, and the trunnion that your shaker is sitting on can only compensate so much for this center of gravity wanting to go one way or the other, or maybe even out of the screen towards us or back or in any direction radially from that center of gravity. Even worse, you can have a center of gravity that's possibly offset from the actual center line of your setup, and that can get really tricky. So essentially what this does is limits what the drive is to prevent the satellite from tipping over.
It must be a great feeling when you're testing a $300 million satellite. No wonder why they're making these small cube satellites now.
Oh, yeah, nothing will make you sweat more than being the guy that has to press the go button when you're testing a multi-million-dollar satellite. Something goes wrong, you know somebody's getting fired, right? So
a lot of people will be deprived of satellite TV too. It's just a tragedy.
Yeah, how awful for them. So moving on here to regular data reduction. So again, we've talked about the controller part of things. Now we're going to talk about this reduction system. This is how this works. We've got some kind of input controller card here on our SCADAS lab chassis that has all these channels. And the main controller has these two outputs. One output goes to the shaker amplifier. This other output is going to put out this COLA signal that gets plugged into the tacho signal, the tachometer on your recorder system. And COLA, again, stands for constant output level adapter or analog. And what this essentially means is it's going to send a constant voltage signal out to this tacho so that the recorder knows exactly what frequency the controller's at and can then apply that filtering that we talked about before. So with the harmonic estimator, you need to know what frequency you're at or driving the shaker at to be able to suppress the harmonics. Otherwise, you're just guessing, right? So this is how the recorder knows what the controller's doing with this tacho. And that's all you need to do to be able to synchronize controller and recorder with the SCADA system. So on the controller interface, you'll check the box here to output the controller and output 2 in the Sine setup workbook. And then in the SCADAS recorder, you got to make sure to enable the tacho 1 channel to pull that data in. And then essentially what we do here is convert that into a frequency versus time plot. And that allows us to know what frequency we're at and apply that in any live or post-processing of the incoming data into the system. So a couple reasons, again, touching on this, why you might want to do a secondary system. One of the main things that you can do is start recording data from the amps turning on until the amps turning off on the shaker. So you get all this self-check stuff, you record any transients that might happen during the test that you might not catch when you're just starting, when you start excitation, the shaker. So especially when you're testing very big, expensive satellites, you might want to know all this information, what's going on in self-check, how that compares to the amplitudes during the test, et cetera, et cetera. And you might tee off some channels from your main controller and plug them into the recorder. You can power IEP sensors with the recorder, of course, and you can also just record time data and then post-process it in offline data reduction. If you're not interested in seeing what any of this is happening, you can then sample at higher frequencies than the controller does. The controller is always going to set the sampling rate to the frequency of the test. You can set an oversampling factor in the software, but it still is linked to the main sampling frequency. So you can set a 2 times oversampling factor, but that's still going to be 2 times what the recording, what the controller is sampling at based on the maximum frequency, the sine sweep. So you might want to get some type of specific sample frequency and can set something kind of arbitrary in a pure time domain recording. Arbitrary compared to what the controller sampling frequency is. One of the other things that you could possibly do is get some more choices in signal conditioning if you want to apply some of the other input cards that Siemens has to offer. Not all the input cards are capable of being used for sine control in a controller, but any of them can be used to just record data. So that the online sine data reduction, you set up kind of like a sine test that has all these parameters like the sample frequency and the estimator method. And one of the other things that's neat about the online sine data reduction instead of just recording is you can set abort profiles. What that'll allow you to do is if you have an abort profile in the secondary system that gets exceeded, it can send an abort signal to the controller to signal it to shut the test down. What you end up getting with sine data reduction is this processed spectral data in the same way as if it's processed by the controller. If you're just doing typical auto power spectra, which is a sample, a block by block kind of method in the standard analyzer, you're not really going to get the same result from a sweeping sine wave that you would in the controller because of the way that the controller actually works in, okay, we know what frequency we're at, so we're going to plot an amplitude where that frequency is. You can get pretty close by using a peak hold method of averaging, but still post-processing time data in a standard analyzer is just going to give you basically FFT analysis, which is not really what we're doing or what a sine controller is doing. It's not taking a block of data and doing an FFT to get a frequency and an amplitude. It's applying one of those estimator methods that we discussed. It's kind of important to understand that when you use this sine data reduction, you get this perfect match. When you don't use sine data reduction, you get something different.
So it's like a composite of many different measurements at different frequencies. It looks like a single spectrum, though. Wasn't taken all at once.
Correct. This spectrum that you deal with sine data reduction, or your sine controller, isn't kind of our standard spectrum that we talk about in digital signal processing, right? Because what that's going to do is take one block of data and do an FFT and get you a spectrum. And in sine, you're going to end up with a spectrum that's basically zero until the frequency you're at, and you get a spike with the amplitude. But what happens when you have this sweeping excitation is you end up with a whole bunch of different spectra that when you average them together, you're not going to get an amplitude per frequency result. You're basically going to get all of those spectra averaged together. And so when you average together a spectra at 10 hertz with an amplitude of 1G and 100 hertz with an amplitude of 1G, and the rest of that spectrum is essentially zero, you're going to be reducing those amplitudes. You're not going to get what the true amplitude was at the frequency. Does that make sense?
Yeah, I kind of like it. This
Kind of
very
like this,
focused
right?
single frequency at a time, huh?
You get one single frequency, and you're taking a bunch of these FFTs, and if you try and average these together, you're going to reduce what this actual peak was because you're essentially averaging in some 0 point here. So you're going to get a reduction in amplitude.
That's what we don't want to do.
That's what we don't want to do in sine. We want to know exactly what the amplitude was at exactly what the frequency is. So that's why we have this time domain method where we're looking in the time domain. We figure out what this frequency is, what this amplitude is, and this gets plotted at whatever frequency this is.
Yeah, we can kind of grab those peaks individually.
You grab the peaks individually, exactly. I mean, essentially what you're doing is you're applying a bandpass filter constantly to the incoming time domain stream. And as that frequency changes, just plotting the results of that bandpass filter per amplitude. So moving on to this offline sine data reduction, essentially what we're doing is we're relying on a recorded COLA signal that we're going to convert into this frequency versus time. Essentially, we figure out what the instantaneous frequency is, and then in the same way, all the other data channels we're processing into this amplitude point versus frequency, like we just discussed. Here's some settings, and we'll go over this in the software, but this is for some notes.